Now let's see what we can say about the type of the critical point at the origin without solving the system. We're going to use the following facts. So we're going to use that if we have a matrix A with eigenvalues R1 and R2, then the determinant of the matrix is the product of eigenvalues, and trace of the matrix is the sum of the eigenvalues. Okay, so here is the first example. Notice that the determinant of the matrix is negative, and if the determinant is negative, it means that we have two real values, eigenvalues of opposite sign, right? So therefore, one positive, one negative eigenvalue. So this is a saddle point, and it is unstable. So we don't have to plot it to deduce that the origin is a saddle point and it is unstable. Now my next example. So here the determinant is positive. So if the determinant is positive, then, well, the sum of the eigenvalues is positive, but notice that here the matrix is symmetric. So, and if the matrix is symmetric, it means that eigenvalues are real. It's a theorem from linear algebra, right? So the product is positive, but the sum, the trace of this matrix is -5. So it's negative. So if the product is positive, but the sum is negative, so it means that they are both negative numbers. So two negative eigenvalues, we have asymptotically stable node. Here is my next example. Now the product of the eigenvalues is determinant of A, so this is 15 minus 8 is 7. So the sum of eigenvalues is the trace, is 8. Well, but if this is the, so if the sum is, sorry, if the product is positive, it means that, and the sum is positive, then we could have two different cases. So either the eigenvalues are both positive, or they are complex numbers with positive part, the real part, right? So we need to figure out whether they are actually real or they're complex. Well, and in order to do that, we can write the whole characteristic polynomial, because the trace and determinant are just the coefficients of the characteristic polynomial. So the characteristic polynomial in this case is r squared minus the trace A times r plus the determinant. So then we find the discriminant of the characteristic polynomial, and then the answer is positive. So since the discriminant is positive, we have two real eigenvalues, and hence both of them are positive. So this is an asymptotically unstable node, or a nodal source. So here is one more example, and then if we repeat, so the product of the eigenvalues is 5, right? 1 plus 4 is 5. The sum of the eigenvalues is 2. So which means that they could be two positive numbers or two complex conjugate numbers with positive real part. But then the characteristic polynomial is r squared minus the trace r plus the determinant A. So the discriminant of the characteristic polynomial is negative here, so therefore the complex values are going to be complex, and we don't know how to, what to do in this case yet. So the next week we are going to learn. So one more example. In this case, notice that the matrix is diagonalizable, but the eigenvalues are equal, so which actually means that it's pretty simple. So if the matrix is diagonalizable, it means that well, it is very simple. So essentially, notice that our system of differential equations is not a true system, so it's just the two individual equations. So it's dx1 dt equals minus 2x1, and dx2 dt equals minus 2x2. So in other words, the x1 and x2 are not related to each other. So it's and this is So these are two unrelated differential equations rather than a system of differential equations. So in this case, we say that we have a proper node at the origin or a start point. In this case, it is asymptotically stable, but if we reverse the sign of the eigenvalues, then it would be asymptotically, it would be unstable. Okay, so let's look at what we've seen. So with homogeneous linear systems of two differential equations with constant coefficients, right? So to determine the type of the critical point at the origin, so notice that we are assuming that the determinant of A is not 0, because if it is 0, then it means that the origin is not a single isolated critical point, but that there is a whole line consisting of critical points. But anyway, so to determine the type of the critical point, we need to find actually we don't need to find the eigenvalues precisely. So what we so we know that if the product is negative, then it's a saddle point. So if both of them are negative, then we have asymptotically stable node. If both of them are positive, then we have an unstable node. If they are equal and there are two independent eigenvectors, then the matrix is just a diagonal matrix. So then we have a proper node or a start point. Well, but if we only need to determine the type of the critical point, so in other words, we don't need to solve the system or to sketch the phase portrait, we don't have to compute R1 and R2, so we can do it like this. So we can figure out whether they're real or complex. If they're complex, then the next week. If they're real, then we can just figure out whether they're positive or negative from determinant and the trace of the matrix. So then if they are equal and there is only one linearly independent eigenvectors, which means that the matrix is not diagonalizable, that's the trickiest case. I mean, not probably. We are not going to learn it. You can read about it in the textbook. So then what we haven't covered yet is what happens if the determinant of the matrix is 0, and then I suggest to figure it out at home and share you via discussion board, I mean, as comments to this video. Okay. And then if we want to produce some more or less accurate sketch of the phase portrait, then not only we need to know the signs of eigenvalues, whether they're positive or negative, but we also need the eigenvalues themselves and eigenvectors.